Hi, my name is Lynn Wan, and I'm an undergraduate researcher under Dr. Gallahan. Today, I will be presenting my research topic on the effects of diet-induced acidosis on the mTORC1 pathway and muscle protein synthesis. So I'd like to start off with the introduction and research question. So the Western diet has become increasingly more acidic due to higher intake of fat and protein, paired with the decreased consumption of vegetables and fiber. Because of this, alkalinity in the body is reduced, which may lead to diet-induced low-level acidosis, and that would ultimately hinder muscle protein synthesis. And often this process increases the risk for injuries in obese individuals and older populations. While it is unlikely that diet trends will change in the near future, we are still interested in determining whether increasing the pH of protein components in a diet will mitigate the muscle loss associated with acidosis. So our approach for observing these effects is to conduct a mouse study for obesity and compare casein protein at a pH of 9 against casein protein at a pH of 7. And the pH of 9 is achieved by putting the casein protein through an antimicrobial step, which entails adding ammonium hydroxide to it. And casein protein at a pH of 7 is done by neutralizing it after it has undergone the same antimicrobial step. Just for reference, the antimicrobial processing step is done in normal foods that we eat every day. It's just for preservation and to prevent bacterial growth during storage. Also, for humans, the average physiological pH is approximately 7.4, and that's similar to that of the C3H mice we will be using in this study. So for the background, I want to talk about the mTORC1 pathway that this hypothesis is based off of. The mTORC1 pathway is the main contributor to muscle protein synthesis and is directly affected by extracellular pH levels. And during diet-induced acidosis, upstream components of the mTOR1 pathway are inhibited, which causes a reduction in activated downstream components. This also includes inhibition of mTOR protein, which would otherwise contribute to protein synthesis. Some inhibited upstream regulators would include RAF, MEK, and ERK. And some inactivated downstream products would include 4-BP1 and S6K. And here's a diagram for the mTORC1 pathway. It specifically contributes to protein synthesis at the bottom here. And you can see the phosphorylation steps. The arrows represent activation. The lines with a flat end to them represent inhibition. And so lowering the pH would inactivate RAF, which would inactivate MEK and ERK. And once these are inactivated, TSC1 and 2 are no longer inhibited, which would mean that this protein inhibits RAGB, and that would prevent the mTOR protein from running, as well as activating its other downstream components. So for our hypothesis, I want to talk about, we believe that increasing the pH of casein protein in a diet fed to mice will result in greater muscle protein synthesis, which will be measured in lean mass, in comparison to a diet with casein protein at neutral pH. We also think that a lower pH protein component will inhibit the mTORC1 pathway in comparison to a higher pH one, which negatively impacts the preservation of muscle mass. Our objectives include determining weekly changes in mouse weights over 7 months for mice who are fed a low-fat diet with casein protein at pH 7 and pH 9. And then we will analyze their lean mass versus fat mass with MRI data that we collect at the end of 7 months. Then we will perform necropsies, which are done biannually. So we just finished our first round of necropsies about a month ago, where we harvested skeletal muscle tissue for analysis of mTORC1 inhibition by Western blotting and for observation of structural differences in muscle tissue by histology. And these are the materials and methods. This is the procedure that I was talking about in our objectives. So first, we split 128 mice into two large groups of 16 cages each. So group 1 has 64 mice split into 16 cages, so there are 4 mice per cage, and that's the same for group 2. I also want to note that in the 16 cages, half of them, so 8 cages are females, 8 cages are all males. And the mice in each cage are identified with hole punches in their ears. There's none, right, left, and both. So none would be no hole punches. Right would be in the right ear, left would be in the left, both would be in both. And this is relative to the mouse. So it would be opposite of my right or opposite of my left. We feed the two groups the following diets. Group 1 has the ammonium hydroxide enhanced diet, which renders it at a pH of 9. Group 2 has the neutralized diet at a pH of 7. And we would weigh and refeed the mice weekly, record their total mass and food consumption in grams in an Excel sheet. And we take MRI scans monthly. So in that, we took the data and we compare the following between the two groups. The change in percent composition of fat mass and the change in percent composition of lean mass. And so we are looking at the percent composition because we want to account for the differences in weight gain. We just want to look at how much of that additional weight gain is made up by the fat mass and lean mass rather than just looking at the percent change by itself, because mice could gain more weight than the other group, but that additional amount of weight may not be made up as much by lean mass or made up as much by fat mass. So that's the reason why we chose to do change in percent composition rather than change in percent. After we did the MRIs, we necropsied some mice following the animal care and use protocols. And we harvested skeletal muscle tissue from the right quadriceps of them, and collected tissue is separated and labeled according to their group, cage number, and hole punch ID that it belongs to. And the tissue is placed into 1 microcentrifuge tubes for protein analysis and 2 histology cassettes for structural analysis. And we haven't gotten to this part yet because we are still only halfway through our study, but eventually we will take the microcentrifuge tubes to be used for Western blotting, and there we will stain for ERK, 40BP1, and mTOR. So for our MRI results, I included these first two figures, figure 1 and 2, to show the total mass as well as the proportion of that total mass made up by the lean mass and the fat mass. So this is group 1 and this is group 2. You can see here that group 1, their lean mass started to make up a smaller proportion of their total mass, especially towards month 7, and their fat mass proportion increased as well. We compare this with group 2, which is at the neutral pH. Their lean mass did also end up making a smaller proportion of the total mass, but it was not as drastic of a decrease as group 1. And group 2's fat mass proportion actually decreased towards month 7 in comparison to that increase that we saw in group 1. And I also included these bottom two figures for a close-up view when we were comparing lean mass of group 1 versus group 2 and the fat mass of group 1 and group 2. So we can see that past month 4, the lean mass of group 1 looks to be decreasing at a steeper rate than group 2, which would account for why the lean mass proportion up in figure 1 for group 1 is less than the lean mass proportion of group 2. And in figure 4, we see that the fat mass for group 1 increased at a greater rate and decreased at a lower rate than that of group 2. Again, that accounts for why the fat mass proportion of group 1 seemed to increase while the fat mass proportion in group 2 decreased. I also wanted to include a statistical analysis table. I compared the change in percent composition of lean mass between both groups, and the p-value was 0.006035. I also compared the change in percent composition of fat mass, where the p-value was 0.000143. So from these results, it showed that the PH7 diet resulted in a higher average gain in percent composition of lean muscle mass than the PH9 relative to their average total mass gain. Also, it showed that group 1 resulted in a higher average change in percent composition of fat mass than group 2. So for now, the MRI results do not support our hypothesis that a more alkaline diet results in higher muscle protein synthesis. And this may be because a higher pH causes the Cori cycle to be less effective in synthesizing ATP for muscle protein synthesis when we compare that to the neutral pH, especially when an already optimal diet is already being implemented. So this optimal diet would be the one that we were studying, which is a high protein, low fat diet. So because of this, the low fat diet will be our control group when going on to study high fat diets. For future directions, once training in histology is complete, we expect Western blotting to show that the low pH group will have more inhibited ERK and mTOR, as well as more inactive 4-BP1 compared to the high pH group. The results of this project established data for a control diet that will be used for comparison against high-fat beef diets and analyzing the effects of pH on muscle protein synthesis. And so once we do study these high-fat diets, it's possible that the results we expected to find in this study could be observed in the future ones with the high-fat diets. Lastly, I just want to say thank you to Dr. Galahan for guidance in collecting data and this research topic, as well as for constructive edits in this poster. I'd also like to thank you, Dr. Minik Dewella and Dr. Mustad Musa, for providing the diet feds to each of the mice group. I would also like to thank Elizabeth Saucedo, Jaden Hendricks, and Cameron Parr for helping me collect mouse data such as weighing and feeding, MRI results. And finally, special thanks to Empirical Foods Incorporation for supporting this research and training project. Thank you.